Imagine a photo buried under heavy static, like an old TV tuned to a dead channel. You can barely make out the shapes underneath. Now picture yourself slowly dialing back the noise bit by bit until the picture emerges clearly. That's a diffusion model in a nutshell. It reverses the noise process, starting from pure randomness to sculpt something coherent. In generative AI, that data might be an image, an audio waveform, or a text sequence. The model trains on millions of examples, so it knows what natural data looks like and how it appears buried under noise. By learning to clean the noise, it learns to create. Diffusion models completely changed generative AI when they arrived in 2015. They work through a two-phase process that flips creation on its head. The forward pass slowly drags a real image through dozens of steps until it dissolves into pure Gaussian noise. This step is completely deterministic and trivial to calculate because you are just adding noise. Then comes the reverse pass, where a neural network learns to strip that noise away one step at a time. Starting from pure static, it works backward to reconstruct a crisp, realistic image. Run that process long enough, and you will hold a completely new piece of data that perfectly matches the original training distribution. The real breakthrough is that teaching a network to remove noise step by step is vastly easier than forcing it to generate a whole image in one shot. The model tackles the problem by running thousands of tiny denoising steps. That steady grind keeps it on track and stops it from spitting out gibberish. Generative AI exists for one thing. It builds fresh content that mirrors the patterns of its training data. The system absorbs the distribution and outputs something entirely new. Discriminative models just ask if an image is a cat. Generative models ignore the question entirely. They build the cat you asked for. It generates photorealistic photos alongside artwork and product mock-ups. The system writes articles and code while drafting summaries and creative pieces. It composes music and synthesizes voices for audio before producing animated clips, visual effects, and deepfakes for video. It also maps protein structures and designs molecules. Researchers use it to discover entirely new materials. The system turns raw scientific data into breakthroughs. You feed the model thousands or millions of training examples, and it learns to generate anything inside that distribution. That simple loop powers every modern AI generator. A few architectures rule image generation, and diffusion models sit firmly at the top. They completely overshadow the rest. DALL-E, Midjourney, Stable Diffusion, and Adobe Firefly all run on diffusion architectures. That shared foundation powers their best work. They have become the gold standard for photorealistic image synthesis. Their iterative denoising process delivers stunning detail and total control. GANs, or generative adversarial networks, were the previous dominant approach. They work by pitting a generator against a discriminator in a constant adversarial game. Variational autoencoders compress data into a latent space and sample straight from it. They still power style GAN applications, but diffusion models now dominate for image quality. Flow-based models use invertible transformations to compute exact likelihoods perfectly. They excel at structured generation, but just cannot match diffusion networks when chasing photorealistic detail. This model shows real promise, but stays far from mainstream production image generation. The model behind every image generator you actually use is a diffusion model. You can almost bet on that. Fine-tuning starts with a model that already learned the basics from massive data. You then train it further on a smaller specialized dataset to master a specific job. Think of it like this. A diffusion model trained on millions of general images instantly recognizes edges, textures, and shapes. It completely misses your product line, your art style, and your brand identity. Fine-tuning closes that gap by teaching it your exact style without starting from scratch. Low RA stands for low rank adaptation, and it currently dominates fine-tuning for diffusion models. Instead of rewriting every single weight, it injects small trainable matrices that lock in your new concept. You only need a handful of example images to make it stick. Full fine-tuning overwrites the entire model with fresh data. That raw power demands a heavy budget and easily breaks on small datasets. Newer approaches skip weight adjustments and fine-tune prompt embeddings or conditioning layers instead. This clever middle ground delivers faster training without sacrificing image quality. Fine-tuning lets you train a diffusion model to nail your exact visual style. It learns your brand logo and product aesthetics, so every output stays perfectly on message. Large language models like GPT Claude or Gemini take a completely different approach to generative AI. They build text token by token using autoregressive transformers instead of running diffusion processes. They share the same generative DNA, but split completely on architecture and creative domain. LLMs rely on autoregressive transformers to predict the next token and build text. Diffusion models flip the script by using denoising networks to strip away noise and reveal images or audio. They are finally converging. Multimodal models pair a language model that reads your prompt with a diffusion engine that paints the result. The top generative systems in 2026 run on both. Diffusion models power the generative AI revolution you see every day. They learn to strip away randomness and turn it into reality. It is a surprisingly elegant trick. You want to generate images or music or even scientific data. Diffusion is the architecture you will always reach for. Fine-tuning methods like low R-ray let you tailor these models for exact tasks. You skip the massive retraining from scratch and get straight to the work. Generative AI is shifting from showing off to giving you superpowers. Diffusion models will keep evolving, and they will do it faster and smarter than ever before. How does a diffusion model actually work in plain English? It simply learns to run that noise process backward. It starts with pure randomness and strips away noise step by step until a realistic image emerges. Imagine slowly wiping static off a television screen until the broadcast finally appears. The machine has just built something real from nothing. What exactly is fine-tuning, and why should you care about it? Fine-tuning takes a general model and tailors it to a specific niche. You simply train it on a smaller, focused dataset. The result is a specialist rather than a generalist. Techniques like low R-ray let you train a whole new model using just a handful of reference photos. You get brand-specific or style-specific or domain-specific generation without rebuilding from zero. What single architecture actually runs modern image generation today? Diffusion models took the crown. They pushed GANs and VAEs to the sidelines while becoming the standard for image synthesis. The whole industry runs on DALL-E Midjourney and Stable Diffusion now. If that made it click, subscribe. We break down the frontier of tech and AI every day.